So linear approximations and differentials. Check it out what I prepared for you. Do you remember, let me see first if you remember. Do you remember this cool limit you had in the homework? It's called special limits. Sine x over x when x approaches 0 is 1. So we had it in my culture, we call it a wonderful limit because it's a special case. In American culture, we call it special limit. So that means that around 0, so this is a ratio. How fast sine x is around 0, how fast x is around 0, and then the ratio gives you 1. That means they're the same, or at least close to be the same, around 0. Check it out. Here is line y equals x. You can draw it if you want. This is actually a pretty cool idea. Y equals x, and then y equals sine x. Here they are. And they are very different everywhere, except over here. Not just at 0. Seriously? Not just at 0, but periodically, of course. So plus 2 pi, and also here, if you want to look at those cases too. When I zoom in, you see the green line and sine. You cannot distinguish them anymore. You still can distinguish them here, but the closer you get to 0, here's my interval of 0, say minus 0.003 to plus 0.003. Around there, line looks the same as sine. That is surprisingly much more phenomenal than you can imagine. So let me show you some cool stuff. Here it is. I draw it in Desmos, and now I'm gonna zoom in. Zoom in. Look at this. Where is sine? Where is line? They are the same. Do you know how hard it is to work with trigonometric functions? You do, because you do it in your homework. But it's very hard to work it when it's your job. When you have STEM job and you work with trigonometric functions, even with computers don't like tricks. It takes lots of effort for it to work with tricks, calculate it. It gives you errors, lots of waves happening. They give you some infinities and so on. So instead, people use lines when they can. That's called linear approximation. Instead of sine, why not to use line over here? If it's the same thing, you just don't go far from 0. If you stay close to 0, you see minus 0.4 to 0.4. That's what it says here. Stay close to 0, then instead of sine, what is sine of 17? I don't know. But what is x at 17? Guess what? It's 17. Isn't it cool? That means, well, 17 is not close to 0, though. So my point is, you can check that sine of 0.4 is very close to x equals 0.4. Isn't it cool? So, yeah, we actually can check that. I can literally just zoom in and check. Here it is. 0.4 at y equals x gives you 0.4 exactly. Sine gives you 0.397. That's how close it is. So it will give you an error. Remember, limit doesn't mean they're equal. Limit means they're very close as you want, around 0. So it's a limiting position. But isn't it amazing? If you don't care about this 5th digit difference, that's what you call it an error of your calculations, and you use the approximation instead. This is how it looks. TikTok. Not TikTok in class. You can do it later. So here's how it looks like when you approximate. They're zooming in. This is not even sine in this case. This is just any kind of function. And we're going to learn to do linear approximation of any kind of function. See, they're zooming in, zooming in, zooming in. If at some point line is close to the graph you're working with, why not to work with the line instead? Because you know what? Lines are easy, while logarithm of sine x divided by square root of arcsecant is hard. That is a genius idea. And those genius ideas were used in space science and still use. And Americans sent their first astronaut to space using these ideas. And that's where the Hidden Figures movie comes into the picture. So, the homework is ridiculously boring, just letting you know. And that's why I like to make at least class interesting, because the homework will not be excited at all. But I wanted to have like a really cool introduction. You definitely should watch the movie Hidden Figures. It's real, it's historical event and so on. But if you search Wikipedia about all these events happened in hidden figures. So Catherine used Euler's method in the movie, and it's true, she did in real life, that determines the rocket's trajectory for the Mercury Atlas 6 mission. For you to know, it's hard to predict where the shuttle or space shuttle will land on Earth, and that's what was the problem. Okay, hitting moon is one thing. Going to space, easy, space is everywhere. But coming back and not killing a person inside of that box, that's hard. So they know that it will be going back, but while it's going back, the Earth is moving. And then the wind is blowing, and the rocket is also moving, and so on. So it was hard to calculate. And what they did used Euler's method, which is also one of the many methods of approximation. So here how it looked like in Wikipedia. This is the real documents from the Wikipedia and scientific articles they used. See though your theta you don't like? See, it's everywhere, the theta, everywhere. And lots of derivatives, you see the derivatives, we're gonna do this today. Those are signs of approximation. So we went, all the women of math department went to watch this movie together. So it was a whole room full of math women from the department. And then when they mentioned Euler's method, we would start screaming that it's like a really good idea. And then everyone else was very surprised why we're so happy about the math. So we were happy about the math. Very good. So before I introduce you to formulas, let me show you this again. Any kind of function, sine is just a very famous example. It's a known case. And then you have a tangent line. Here you go. Is it close? No, like look at those gaps. Those are horrible, not close at all. But let me zoom in. Okay, it's getting better. Let me zoom in more. Okay, getting better. So that means around the point, you can use linear line. You can use a line instead of a function. So that's called linear approximation. And this difference over here, we will be calling error. Here it is. That's like this gap is like whatever you have to show to people that I'm approximating the function and the error is like 0.03, 0.0015, or even a function. But you know, you not always can do that. Here's the example of a function. Zooming in, everything is horrible. So then it means the function have to be smooth, like sine or like parabola, or just like nice smooth function, which means what we don't like. How would you call this shape? Sharp turn. Cusp, they call it in English cusp. It's a sharp corner, sharp turn. We don't like that. So it's not helping when we zoom in at the sharp corners. It's still sharp. So when I put a tangent here or here or here, it's not going to work. Thus, do you know how would we define the rule then? What kind of condition we should put in the function in order to use these methods of linear approximation? If we don't like sharp corners, what does it mean we should make sure? The function should be differentiable at the point. Do you remember what it means to be differentiable at the point? It's not a tricky question.
The left-hand limit equals to right-hand.
Yes, limits, yeah. Polynomials are all differentiable and nice, but my question is very simple actually, don't overthink this. It has a derivative at the point. Differential means it has a derivative. So we're gonna have to have this important requirement. So let's write it down. Here you go. Here's your formula, write it down. 2.8, the theme is linear approximation and differentials. Linear approximation of a function f at a. So we're trying to approximate using a line. That's why it's called linear approximation. Suppose function is differentiable at on the interval. On the interval means at every point of that interval. The linear approximation of f is given by a function. Capital L, that's classical international notation, is f of a plus derivative f of a times x minus a for x in I. I is the interval. It's very popular notation for the interval. So, to explain that, let me just remind you that f prime at a, that is your slope m, x minus a, that's x minus x sub 0 we usually have. F of a, that's y sub 0 we usually have. So let me write this down if you want. Y sub 0, x sub 0. And that takes us to a very known formula we knew before. And I'm going to write it down. Equals L of x. L is approximation. So, because it's approximation, you can write down that f at a, the original function in f at the point a, is approximately capital L at a. Let me see if I can put, sure, like so. Or in the whole interval. So equal sign here means we're defining linear approximation, but then it's not exactly equal to original function. That's the whole point. So, I would say like x. Let's keep it x. X and x, like this. On I. On the interval I. So f will be, sign can be approximated with x, y equals x, on the interval around 0. Did you finish writing it down? Thank you, thank you, thank you, thank you. Let's write down what we know. We know this formula, how this was even created. Y minus y sub 0 equals mx minus x sub 0. We knew that. If you don't know that, you're like kind of behind by a couple of years already. It's fine, but know it now. M is a slope, point is a given point, x sub 0, y sub 0 is given. So from there, we rewrote everything in terms of f. So that's how they got it. IA, how do you know what IA is? Like, which means, let me write it down. That's the English notation, IA. That is. IA means that is, right? I like it because it's short. How do you actually describe it? What is I and E? What is I? Yeah, nobody knows.
It's Latin.
Latin? So that's, okay. Let's not talk Latin. I don't want to summon some demons accidentally. F of x, that's my y, minus f of a, that's y sub 0, equals slope m, f, that's me, and then you just do x minus a. So we rewriting it. I don't really do anything new. We're just rewriting it. A was described as x sub 0. That's the only thing that was changed. And y is f. Then, check it out. We will have f of x equals, many of you writing it down already, this way on exams, I saw it. F of x equals, I'm gonna move f of a to the right. It's going to be f of a plus m x minus a. That's what we're gonna still move, and then we're gonna have this formula. So the only thing is new now, need to be changed, is f prime at a. So m is your derivative at a. That's your slope. That's your slope. L is approximately, and we're gonna do like this, fat, approximately L. And I'm gonna put it in the box. This right-hand side gives you approximately L. But you see the left-hand side and the right-hand side, f of x is approximately L. That's what's important. So we're gonna use line to approximate the function. So I'm gonna using line to approximate APP-ROX. That's what I will keep it. The function. And that's why it's called linear approximation. Very cool topic. When I was learning it as a student, I did not understand how cool this topic is until I got to graduate school and we started working on this. Yes?
What exactly is L?
What?
What exactly is L?
Oh. L, very good question. Yeah, thank you for asking. L is linear approximation. So, oh, I guess you're right. That's the let's do it this way. It's equals to L. M.
Is that a constant?
L is this all box here. So it's an approximation. But L tries to get close to f of x. Yeah, I think that's correct. So let's just keep it this way. Yeah, I think that's the best way to explain. F of x is approximated by L, like so. On the I, yes.
Is there some way to quantify the error, to like put a number to it?
Very smart. How can we gonna figure out the error? We're gonna do it right now. Very smart. Quantify the error. I like this terminology. Yeah.
So L is the equation of the line that we're using to approximate?
Yeah. Should write this down too. That's very good explanation too. L is equation of the line. And then at the equation of the line is lane. Over here, like we don't like it here. Look at this horrible gap, and here. So that's why we only care about the equation of the line around the place we care about. And that's why we're using tangent line. That's why the slope matters here. The slope is where the line touches, kisses the function. And that's where you zoom in, zoom in, zoom in. There, it's very close to a function. And then you can use this as a linear approximation. Yeah, very good questions, people. Good job. Let's do, the error. Let's define the error. Error. E. That's classical notation. Everyone called E because of the error. Absolute value because you don't want to have error minus 0.5%. No, you want to have a number. Guess what it is? It's exact minus approximate. That is not very surprising. Minus approximate. That's the dumbed-down way to learn what error is. There's a whole chapter, there's a whole part of mathematical computational science called computational mathematics, numerical analysis, where they have so many methods how to do approximations. Euler method, which they used in the Hidden Figures movie and actually in real life, it's one of the so many methods. Euler was just very smart, and he figured that method that always works nicely. But then they improved it, and now Euler's method is not always the best one. So you use different methods for different cases. That's also very interesting. So if you ever want to go to the numerical part of the math, computer science part of the math, it exists, called computational mathematics. They have so many cool programs and codes, and they prove the theorem that the code works always. That's how cool it is. You can prove that your method or the code works. Because computer scientists, or data scientists, they use the code and it works and they give results, which is amazing. Mathematicians prove if it works always. And if it does, what's the error? How cool is that? So if you want percentage, you multiply by 100%. That's percent error. You will see it too in the literature. Percent error. Percent error. Do you have questions about this? What do you think about this thing? Percent error.
So if you're majoring in CS, we will have to learn this in depth eventually.
Yeah. In computer science classes, you will learn lots of stuff. They will be pushing more into methods, coding them and finding errors. And in math major, we push more understanding of why it works and when it doesn't work. So again, you use the code, but did you ever consider that the function is not continuous? Did you ever consider it has a cusp? No, because the book tells you it works, so you work. But the deep understanding behind, that's what makes people getting their PhDs, making amazing discoveries. And then practical side of it is the computer science part. Yeah.
Would it be times 100% or times 100?
What do you guys think? Is 100 or 100%?
Times 100, just 1% is just the...
Yeah.
Percent is just outside unit, yeah. I think that's what they meant in the formula. Probably there was like parentheses here originally. Good point. Yeah, good point. Thank you for mentioning that. So nobody wants to ask like a very obvious question. There's like elephant in the room. The students always ask this question while I'm writing down the example from your homework. There's no obvious question coming. There's a weird stuff happening here. How come nobody's curious? Example, without using a calculator, find. Maybe this question will happen after this example. This is what you have in your homework. The most freaking boring question you can ask. It's even more boring than why you have 35 watermelons in the problem from the store. Why do you need 35 watermelons? This one says calculate without using a calculator. It's fine using a calculator. Find, I guess. Or calculate. A, what is sine of 0.17? B, what is sine of minus 0.8? C, what is sine of 1? Well, that is the idea. And in your homework, you also have square root of 37. Who cares? So it feels so fake in your homework. Why they want you to find square root of 37 without using calculator? What is the problem with these problems? Also be careful. When you calculate the sine of 0.17, don't forget to change to radians or change between radians percentage. That's why you get wrong answers in your exam sometimes. Don't trust your calculator too much. But the idea is we can do that using linear approximation. So we know solution. Use linear approximation. Why not? Since they want us not the exact answer, and they already said that you should not use the calculator, so we're gonna proceed with the formula. Yes?
How do we know if they want us to find it exactly or if they want us to approximate?
Yeah, good question. Find using calculator.
Would it say
Without using calculator.
without using a calculator?
No, we're gonna learn where methods soon when it is, but not in this class yet. I guess good question. How do they know when they're asking you? Okay, then using linear approximation. How about that? Linear approximation. Like so. In your homework, it's very obvious. On a test, I also tell you, using linear approximation. Use linear approximation. That means they want me to use the formula L of x equals f of a plus derivative at a x minus a, like so. That is the formula. You need to know this formula. You learn it. You're happy about it. You memorize it. It was derived from the known formula you already know, so it's at least that is good. Now, let me show you the steps. Step 1. Let me then do this circle. Step 1. We're gonna find an approximation for what is my f of x first. For all three things, A, B, C. Sine x. So we're working with sine. So now you see it not as a number, sine of blah, blah, blah. You see as a function sine, and we're plugging different inputs for that function. Remember, functions are tools. So the tool was announced, sine x. Then at a, which is, they give us to, I guess, do they give it or not? Yeah, let's give it to you. Or else you will also be confused. Use a linear approximation around a equals to 0. I'm hesitating about this step because scientifically, this is not how it works. Scientifically, you should guess. But in this case, let me give it to you and then I'll explain you that you're supposed to be, as a scientist, guessing that this is a good thing to do. Why this is a good thing to do? Sine x at 0. So all of this, let me underline, is given. This is given. Because as a scientist, you remember that sine has a very good approximation around 0. Not only around 0. So let me show you the graph again. Sine looks like a line around 0, also over here, and also at the next loop. So it's a periodic function. So technically speaking, you can even do shifts by pi and 2 pi. To make a very good approximation. But in this case, I'm choosing that the good approximation will be 0. Do you know why?
Because we already know what it is in 0.
Because we already know what it is in 0, and
It's really close to 0.17 and
It's very close to 0.17 minus 0.8. So you notice the numbers we try to calculate are close to 0. That's also good. That means the error will not be too large. 0.17 is over here. Minus, what was it? Minus what?
0.8.
Minus 0.8. It's over here. And you see, over here, it is very close. The 1 will be kind of awkward. The 1 will be here and there will be like a gap. Not big fan of that, but we will see how it works. Okay, so we need to build this linear approximation. From the previous chapters, you know it will be a line x, but actually let me teach you how to build it for all kind of functions. So we know the formula, we know the function given, and we know the point given. L of x will be, so then L of x becomes f at a, 0, f at 0, plus f derivative at 0, x minus 0. You're plugging everything you know, which is basically only one thing for now, 0. The second thing, you know the function. So you can write down f of x is sine x. You could have skipped this step and write down right away that is going to be equals, it is sine at 0 plus derivative of sine, let me write down first, derivative of sine at 0, x minus 0. Make sense? And you can keep going actually. You can write down it's going to be sine at 0 plus, what's the derivative of sine? Cosine at 0 times x minus 0. 0. All of these are correct. People actually choose where to stop. Some people perform calculations separately. They find f at 0 and then f prime at 0 separately. Instead of rewriting it all the time. What if you have 35 functions to figure out? Then you don't want to keep rewriting it, so you just find it once and then plug into result. F at 0 is sine of 0, which is 0. But derivative is 0 is cosine of 0, which is 1. So you know that. And now we're going to plug it in. Equal sign becomes 0. Cosine of 0 is 1. So it's going to be 0 plus 1 times x. Wow, which is x? What? Are you saying me that L of x is just x? Yes, that's literally what I was telling you at the beginning of the class. Linear approximation for sine around 0 near x equals 0. Let me write down like so. Thus, sine x is approximately x near 0. Near x equals to 0. Note that is why, well, not only because of that, limit of when sine x compared to x, when x is close to 0, they give you the same thing. So the ratio is 1. It's not only that is why, but then we're going to learn other methods to prove this amazing limit, including L'Hopital's rule is coming and so on.
Wait, so if sine x is x near as x approaches 0 basically, would that mean that as limit x approaches 0, sine x is just x?
What?
As limit x approaches 0, sine of x just evaluates to x.
Mm-hmm.
Is that what it means?
Sine of x, oh yes, around 0, sine of x is x.
So if we have a limit that says exactly like sine, limit x approaches 0, sine x, then that's just x, or is that 0?
Oh, good question. Sine of x when x approaches 0 is 0. Limit of x as x approaches 0 is 0. And then your question is what happens, can you rewrite one function instead of another one, right? So,
what do you get when you have a question like evaluate the limit and then you have limit x approaches 0, sine of x. So do we write it's equal to 0 or do we write it's equal to x?
You write it's equal to 0 exactly, or you write it's going to be a limit as x approaches to 0 of x. That's what it means. And they both give you 0. So you cannot write down it's exactly x, it's limit.
Right.
Because it's all approximations.
Right.
Yeah?
So what if we have an example that says find sine 93 and 4?
Yeah, good question. Let's do that too. So let's answer those questions now, which is like super complicated, right? If I'm approximating x with sine x, then what is approximately sine of 0.17?
0.10.
Wow, how do you know?
0.17.
0.17. How do you know? That's so clever.
We just find it out.
Because we just decided that L, which is approximation, is x. Does that make sense? Because sine of x, approximately x, around 0. Around 0. Does that make sense? Or it came out of nowhere? Did you just blink and now it's like out of nowhere? I always like to say, you should ask questions. Don't be afraid to be behind. You know, there's a joke like, oh, you drop your pen and you're like, why are you picking it up? You look at the board, it's like full of notes. It's a popular joke. So, did you blink? Ask me. Yeah.
It will always be approximately, right? It'll never be.
Yeah, L. I mean, I guess if you approximate L with L, that's exact. Line and a line, they match. But everything else is approximate. Yeah, good question. Yeah, it's approximation. So what is this answer? Minus 0.8. Yay! So now we know. 1, I don't know. That's like the hard one. Is it approximately 1? Question mark? Let's see. Why am I concerned about this answer? Why I don't think that's a good thing to say. Like sine at 10, 15. Is it 15? I don't know. So let's check. Luckily, we do have technology now. So imagine you were doing this in older times when Euler was still alive and figured out this Euler approximation, linear approximation. Derivatives were just created. Think about that. No calculators. You have to do it by hand. So this problem is extremely complicated if you do it by hand with no calculators. But now we have tools. So let's calculate error. Double R. 3 R's. Error is E, so let's do for A. E is absolute value, exact minus approximate. Exact can be also mean the best approximation you can have. So if you use your calculator, what is sine of 0.17? So I will do sine of 0.17 minus 0.17. It's not exactly exact, absolute value, because we don't care about the sign. But using your calculator, what does it give you? Sine of 0.17?
0.169.
169. Yeah, let's do like as many decimals as you can. When you work with approximation, do 11 decimals. Or whatever your calculator shows you. 1.8235. Minus, and we keep comparing it with 0.17. 0.17. When you work with approximations, decimals matter. Because you want to know how accurate your result is. That's a good phrase. You want to know how accurate your result is. You presenting this result to people who work in NASA, and I'm not making this up. That's exactly what happened. Catherine was working there as a calculator. In the older times, people were hired to be calculators. And she was a calculator there. She presented this result, and it was used to send a freaking American hero to the space to win the Cold War race with USSR, right? So you presenting this, did you mess up? Yes, there's always an error. The problem is how big it is. So fine, it can be an error, but how big it is. If it's 5 decimal places off, that might be good enough to kill a person because they will land into the mountain. If it's 0.001, it might be good enough that it lands in the ocean. That is. But also it matters if you're talking about microbiology and macrobiology. In macrobiology, when you talk about space science, will my rocket hit the asteroid? The error can be big because the asteroid is big. In microbiology, nowadays, robotics performs appendicite surgeries. So there's a robot thingy and it cuts a person, and because appendicitis surgery is not very complicated and can be done with a robot. Well, 0.001 might be like several cells to the left, and you cut something important. Would you like that arrow to yourself when you are the patient? That's when it's important. Genetics, 0.00001 is important. So it depends on the science you work with. Microbiology is fascinating, but it's very precise. And that's why cancer cells are so hard to regulate, because numerical results give you results, including neuroscience too. But the arrow matters, and it's hard to get a very good arrow. When I was blubbing, does anyone actually calculate that? That is 0.00408. That is my error. And if you want to divide by the original, do you know how to find the percentage? I think I mentioned, right? So if you want to do percent-wise, then you do E% will be, let me quickly redo it, 0.1618235 minus 0.17, that's the one we're talking about, all over 0.1691835, and then times 100. That will give me 5.368% of the original. So that's the percent error. 0.004 looked like fine. 5% doesn't look fine to me. And you talk about the heart surgery, 5% to the left, I don't know. Sounds scary. So 5% chances they will cut your heart and you die. That's kind of a lot. And that's what I'm talking about. But 5% not hitting the asteroid, that's good enough. And we just did it 2 years ago. They launched the first experiment with NASA, and our mathematical graduate students were working there, and they shot the thing, and it did not hit the asteroid, I think. Oh no, I think it did. So it was a big successful, it's called Earth Defense Mission. I can send you the link later. It was all over the news, and our ASU graduate student graduated with PhD in applied math, computational math, working for NASA, doing that. She says it's mostly coding and lots of chemistry, surprisingly, because you need to know chemical reaction of the asteroid, which you don't have in front of you. So you need to guess from the pictures how they look. Is it metal? Is it more Earth kind of style? Is it going to blow up, shattered, just deform, and so on. So the error is whatever is the error. We have that. Let's calculate other errors. Especially, I'm kind of curious about sine of 1. Is sine of 1 actually going to be close to 1 or not? So let's calculate the second one a little bit faster. B. B says, let's calculate E. That is sine of, what is minus 0.88, right? Minus 0.8 minus parentheses minus 0.8 bar. And either you do this one or you do percentage-wise. And if you use a calculator or technology you have, again, it's not an exact answer for sine. That is just the best answer you can have. 0.717356 minus 0.8. And I don't want to care about the sine. The answer becomes 0.082644. Then let me put it in a box. And I don't need the absolute value anymore, actually. Why did I even leave it over there? So answer number 1. Answer number 2. Okay, 0.08, kind of more than the previous one. The previous one was 0.04. But this one is 0.8. Kind of makes it a little bit more dangerous. If you want to calculate percentage-wise, divide by the original to have the relationship with the original, and it becomes 11.5%. Yeah, that's kind of interesting. For the stock market, 11.5% might be actually a good number. If you know something up to 11.5% accuracy, you can invest money in something. But in medicine, I don't know. What do you think about this? We're almost done. Isn't it cool? Yes.
So, when this says that value can calculate, this using an error count as that'd be fine?
Yeah. When you plug into calculator, this comes from like a computer. Yeah. Let's call it a computer. Instead of What we did before was manual approximation, like they did in the previous times with no computers. It was very recent if you think about it, right? What was that year? I should have probably have it here. It was very recent, there was no computers yet, so we did it manually. Now you have a computer, even in your hands. That is the exact answer, which is still not exact, but it's the best one you can have. And we're comparing my answer with the one you have the best, and see the problem. And then you choose which one you like more. Let's calculate the last one. Thank you, yeah, that's a good question. The last one is the one that I'm very curious about, which is sine of 1. Sine of 1. Well, let's have it E, right? E equals absolute value sine of 1 minus 1, right? Well, I'm calculating. My calculator tells me that sine of 1 is 0.8.
Radians, right?
Yeah. What do you think? It's in radians or in percentage? Radians. So you can check in the calculator. And then it's become 0.1, 0.15. That's a lot. If you check the percentage, it becomes 18%. So, you know, would you like to have 18% chances to fail this class? That's kind of a lot. That's the error, right? So I'm going to put it in the box. Does this make sense? Yes, because we know the more away we are from 0, from the left or from the right, the worse the arrow becomes. The more away we are from the point we choose to approximate around, which was 0, the worse my result is. And that makes sense that now it's just too big. Is it too big for your work? As a scientist, you decide. You can still use it, but it makes sense to recalculate the point. It doesn't mean you cannot use it. It means instead of 0, where is my... Exactly. So smart that you got it. Instead of 0, why not just to move closer to 1 or even into 1? Then you find a completely new tangent line. It will be like so. And then you approximate here. Next step, move it again and approximate here. That's Euler's method. On every next step, you actually allowed to move the point of approximation. Or accept the error if that is less hassle, and just accept the error. Yes?
If percentage error requires the actual the actual answer not approximated, and then I'm assuming that's not what you would use if you didn't actually know the...
That's the question. Finally, someone asked the question. There's a big elephant in the room which you should have noticed. That's what I was asking as a student, and then someone asked me when I was doing it. Wait, if we know sine of 0.17 with our calculator, which is computer, right? The best error. Then why we even bother to approximate? What was the point? Why bother approximating if you know exact answer? So they're gonna ask you square root of 37, approximate that using linear approximation. In older times, that was a big deal. How do you know square root of 37 with no calculator? That was a very important question for engineers building houses and so on. Nowadays, it's ridiculous. Your phone knows it. Your phone can give you square root of 37. So why even bother? So it's a big question. Very good. Finally, someone asked. The first question is, in older times, it was fascinating. Now, we don't see it this way anymore. Well, not really. Some functions will be crazy. Some function will have logarithms inside and arctangents inside and so on. Working with them will be a pain, even using computer. As I told you, the computers, they don't really like working with so many different trigonometric functions or quotients. So using lines instead works well. And the other question is, sometimes you know what it should be. So, for example, you know how far the asteroid is, and you're shooting, like in this picture, you're shooting the rocket to the asteroid. The rocket will not be exact. It will not. So here's the asteroid, right? It wants to kill everyone. You shoot the rocket, you know the exact answer. Here it is. It's very specific, from one point to another point. Will the rocket do that? No. Even if it will going like this, there will be wind, they will be changing trajectory, and it might miss it. Sometimes we know exact answer, but it's not applied. It's not real. So you use approximation to find the real answer, it includes waves, the wind, even humidity, even the rotation of the sun at the moment, what sun is, temperatures, minus the exact answer, and then you have your error. And when you catch the good error, you shoot it.
Yeah.
You do it again and again and again. You catch the good error you like, you do it.
So you use it to compare the mathematical, the calculated versus the reality.
Mathematics, yeah. We're using math to compare calculations with reality. Yeah, that's a good one.
But if you are in a situation where you don't know the exact answer, if you are in a situation where you don't know the exact answer, how are you calculating?
If you don't know the exact answer, sometimes you use your calculations as whatever you think is the best. Someone have to start it. Usually pure math tries to use theorems and methods to prove what the exact answer should be. So that's a very good question too. What if we don't know? Yeah. Like in genetics, we used to not to know that there are genes. We used to think that the cell is the smaller thing, or atom was the smaller things. Well, not anymore. So at some point, you create a new exact one and compare to it. Amazing questions. Amazing. Yep.
So I just have a question about one set.